All right, take it away. Thank you.
Thanks. So this is something that we're working on now. It's a pilot, the Storm Tools tool itself actually has been a tremendous boon to us, because when we first started out, we had originally conceptualized a series of static maps. So there would be one map for sea level rise, another for the various surge events, 25, 50, and 100 were the recurrence levels we were using. And then we were going to use combinations of sea level rise and surge and produce a set of paper maps essentially to hand out to the municipalities, but also then have the GIS layers. As we got into the online viewer and we could start to integrate more data into it, it really, it exploded on us in terms of its utility. And we started playing around with it, and thanks to Chris Damon again, Chris has been wonderful about grabbing data sets and integrating it into the system to give us more and more utility as we went forward. As we started to develop that, and another tool that we had actually grabbed and started to develop, which we presented here before, is the Army Corps, after Hurricane Sandy, went into this massive modeling effort and produced a series of grids and storm scenarios for the entire East Coast as well as the Gulf of Mexico. And we grabbed that grid and we've actually downscaled that grid to a 10-meter resolution, and in some areas 5-meter resolution along our south shore. We also have all the save points for those storms, so there's 1,000 tropicals, 100 extratropicals, and we use that now to model the shoreline. So both the modeling capability and then Storm Tools as an online viewer really jumped us in terms of what we could start to produce and give data out. So as you saw, we now have the surge maps, we have the sea level rise maps, and again, based on the North Atlantic Comprehensive Study with the Army Corps, we used ST-Wave to generate significant wave heights. So for each of the save points now, we have significant wave heights for the various recurrence level storms, and those are all on Storm Tools and available to the engineering community. With Brian's work that we've been doing on looking at erosion and erosion maps and also projected shorelines, we have been sort of sitting around the team meetings saying, well, it would be really nice if we could take and sort of compile that data, break the shoreline up into segments based on their geologic morphology, and then start to rank those factors, such as waves, sea level rise, surge, and those types of inputs, and start to come up with an indices of what that shoreline or what its inherent risk is. And it would give us a composite index, but we could always go back and see what factors were really driving that risk. In addition to that, Malcolm had been playing with, from previous projects that he'd been working on for us, looking at a program called HAZUS, which FEMA puts out, but embedded within that are a thing called damage functions. So what the Army Corps has been doing, working with FEMA, is in a post-storm situation, they will go in and they will look at a series of structures. They categorize those structures by type, and then they look at what the surge and the waves have done to those structures, and they start to write algorithms in terms of what the potential damage might be. So with the E91 data that we had, we could start to identify those structures. We had the surge and wave data. Malcolm's group has also pulled in another program called FunWave, which not only gives us a better handle on looking at the waves, but also gives us wave run-up, as well as the actual significant wave heights. And it really is turning into quite. So what we're looking at now is starting to move forward with some of this. And this is sort of an update of where we're at. So we've completed the flood maps. We've completed some of the engineering design tools for the waves. We have an artificial intelligence system that now gives us a very good predictability capability of surge. So before a storm actually arrives, we can actually predict what that surge is and depict it on our maps. We're also working on a river flooding model for the Patuxent River series, which we're going to go into today, and some high resolution wave modeling for inundated areas with dune failure. One of the things that we were concerned with is that the FEMA maps are based on dune failure scenarios that don't really reflect our geologic conditions here. So working with, again, Brian's team, we're taking the dune failure phases that we actually see here and integrate them into the models that we're doing. So that's part of all the work that we're doing. We've got some regional work that's ongoing, and we have now the CERI that we're looking at trying to expand, even though we haven't got this pilot done. And there's also some white papers that have been done to seek funding for an app and a calculator, so we could actually take some of this work and drop it right down on your smartphone, so you go out on site and actually start to run this out on site. So, get into this. So one of the challenges facing us is that we are trying to help municipalities and state agencies look at coming up with some sort of objective way of weighting risk, particularly as it might potentially affect a segment of shoreline. So these tools start to combine together and allow us to start to do that type of analysis. So the building blocks for this are the water levels, the wave estimates, the shoreline change, the damage functions, and also Brian's going to be doing an analysis of the shoreline and breaking it up into segments. And then we also have the E91 database that allows us to look at individual structures. We are also looking at, obviously, the sea level rise scenarios, and you've seen this one already, but you can see the time frames and the sea level rise estimates that we're using for. And so when you start to put this together in into a system, it starts to look something like this. So we're going to have data coming out of storm tools. We're going to have structure and infrastructure data coming out of the E91 database, as well as other work that we're doing. And we've got the wave analysis and surge analysis and the damage that does, the damage function bit at least, that will go into this, so that we can actually now start to go structure by structure, piece of infrastructure by infrastructure, and estimate the damage from any storm or sea level rise scenario and storm. So the area that we started playing with this, and Malcolm took the ocean engineering class and set him to work on this area, is the Matunuck area. It is one that the ocean engineering class had been working on some projects for us anyhow. So it was something for them to really dig into and start to play with it and see if we could really work this out. So these are from the Army Corps Engineers damage function study. And what it does is it categorizes the structures by their various types. You'll see the layout over to the left in terms of the categorization that occurs. And then these are pictures from the actual study area of those various types of structures in terms of where they fit in. So what we're looking at really is, for the most part, at least in the Matunuck area, prototypes 5A on down to 7. And so what this does, and the damage functions start to look at, is principally two types of damage. We have inundation damage or wave damage. The wave damage is obviously done mostly to structures that are very close to the shore, and as you start to go in, the waves start to diminish in terms of their damage, and surge becomes the more active participant in terms of damaging structures at that point. So the algorithms and the models that deal with this will estimate that type of damage based on this. And you can just see here, these are the damage functions actually give you a series of ranges. So you can see the inundation range over to the far left. And then you can see the significant jump done by wave damage. Waves are obviously the more damaging factor in a storm component. And the one on the far right shows you the difference between these. So again, using the infamous pointer here, this is waves, this is inundation. So obviously the waves are the ones that are the most damaging as we go forward. So looking at this, this is the E911 database, so it locates all the structures for us. Then what we can do is start to categorize the structures based on the types that are in the damage functions. So you can start to see the single story, no basement. There's a large cluster here. The stilted structures actually are a very small number and interspersed throughout the community. So that's the distribution, the total distribution by the various categories here, by the structure type. And then what the model really starts to dig into is the first floor elevation. So these are the grades here, the elevation points of which each of these structures are. And all this data was gathered out in the field by the students. So if we look at and in most cases what we have been using right now is a 100-year storm event, because that is the one that's typically used for floodplain mapping. This will estimate the damage for structures. So this is a 100-year event, no sea level. This is a 100-year event with 5 feet of sea level rise. So the red, the color scheme corresponds to the percent damage of these structures. So if you're in the red category, you're 100% damaged, you're gone. The rest of these start to grade out based on their elevation and their structure type in terms of percent damage. And as we see, the damage doubles with the sea level rise. So just again to show you this is a 100-year no sea level rise. This is the total number of structures damaged. With 5 feet of sea level rise, the number jumps and doubles. So we have a 61% increase with sea level rise. So this is a very sort of telling story here. These are two structures from the study area, side by side. And this is what the damage functions estimate for these two. As you can see, if you elevate, you're good. If you don't elevate, you've got a problem. And these are estimates that are obviously looking at the damage. What is really telling here is the basement windows, because once you have a basement window, even though the wave envelope may not, or the surge envelope may not get just to the clapboard, if you've got a basement for it to go in, there's a lot of infrastructure that are in houses, our heating systems, plumbing systems, all the rest of it are in the basements, and these get taken out. The one thing that I'll note about this, and it's a cautionary note, is that these numbers are underestimates of what the actual damage will be, because we have not been able to yet model in wind or damage associated with other structures crashing into some of the existing structures. So if you have a structure that is not elevated and gets taken off its foundation, it will then move with the surge, crash into one, and even if that structure is elevated, potentially take it out. So while this is a very good planning tool for us to start to look and estimate and identify those areas that are truly at risk, it also is a problem for us because it still underestimates the damage that might potentially occur. So this is a tremendous capability because it allows us now to take and do policy scenarios. So if we identify an area, for example, that was damaged severely because of lack of elevation, and we wanted to spend some money elevating those structures, we could then cost that out, go back and run the same storm surge analysis with the damage functions, with that elevation built in, and it will give us a reduction in terms of the damage. We're going to start to associate this back with the assessed values of each of those homes. So it will give us essentially a cost of the savings in terms of value of those structures that we can then use to estimate back against the policy assumptions so that you get a cost-benefit analysis of the various types of measures we may want to put in place. If we wanted to put a protection device in or whatever, we can start to cost those out and look at those. It also allows us to look at infrastructure and look at things like evacuation routes and trying to maintain these things. So it allows us to look at this and start to also cost this out for infrastructure, which we're going to be doing. So the two pilots that we're looking at right now are going to be Charleston and Westerly. Warwick, sorry, it was one of the W's. And we're going to be going forward and using those to do this on a community basis. It is our hope that we can then from there expand it out to the full state so that we can really get a picture of what the economic damage would be from these before it occurs and target areas that would be good for adaptation for a lot of these. So again, Charleston and Warwick are going to be the two communities that we're going to start in.